Welcome to this pilot training module on convective ice crystals developed by Air France. Boeing and Environment Canada contributed to this English version. Until recently, pilots have identified and avoided thunderstorms by steering clear of high reflectivity cells on their weather radar. However, flying through moderate to heavy convective cells is not the only threat. In certain situations, high concentrations of ice crystals may be encountered within the anvil of a cumulonimbus cloud and may not be detected by weather radar. This module will present the current understanding of ice crystals associated with convective clouds. In order to raise awareness of this issue, it will provide a few tools to recognize the conditions and, when possible, avoid them. Even though we'll be talking about ice, what we're presenting here is not what pilots know as icing conditions. This is because ice crystals do not accrete on cold airplane surfaces. This discussion will cover information on thunderstorm avoidance. However, the nature of this icing phenomenon requires avoidance techniques which are different from what has been standard guidance until now. Usually, we avoid storm cells, the source of severe turbulence, by flying around them. It is during flights such as this, in the vicinity of convective storms, where regions of high ice crystal concentrations can be found. At altitude, regions of high ice crystal concentration often have low radar reflectivity and are not detected using the pilot's radar. These clouds typically produce heavy rain below the freezing level, and therefore they can be identified by tilting the radar down to examine returns below the aircraft. These regions of high concentrations of ice crystals in the vicinity of convective weather have now been associated with engine power loss and damage, as well as anomalies caused by TET and pitosensor icing. The effect of ice crystals on engines is not fully understood. Ice crystal icing has only recently been connected with engine power loss and damage. Work is still underway to understand the meteorology and the ice formation mechanism. Thanks to pilot reports, the picture is becoming clearer. Observations in the vicinity of convective clouds have allowed us to make the connection with engine power loss events, TET anomaly, as well as pitot anomalies. Now, the research on ice crystals has focused on the study of engine power loss events. The engine manufacturers and meteorological agencies have conducted research on the nature of the weather associated with engine power loss events. Engine events often occur at the same time as TET anomalies. However, pitot anomalies have been reported at cruise altitude in vicinity of the convective clouds. Both are most likely linked to the same phenomenon. The measured size of these particles is much smaller than previously thought. Recent research suggests that near the convective updrafts of these clouds, particle size is on the order of 100 microns, similar to baking flour. Convective clouds form when warm, moist air rises, cools, and condenses. Above the freezing level, liquid cloud droplets freeze. Convective clouds are very efficient at converting liquid water to ice. Scientists believe that the majority of the cloud in these storms above the freezing level is made up of ice crystals. Ice crystals occur from freezing temperatures to well below minus 60 degrees Celsius. Warm, moist updrafts can transport considerable amounts of moisture to high altitudes, even exceeding the amount of moisture that is typically found at lower altitudes in classic icing. The small ice particles can remain suspended for hours, and upper-level winds can transport the particles large distances, sometimes hundreds of miles. Larger water droplets, such as large raindrops, hail, and wet snowflakes that are on the order of millimeters in size, are efficient radar reflectors. In contrast, High-altitude ice particles, with their small size and irregular shapes, do not reflect radar energy well, even though they are present in high concentrations and form the majority of the cloud mass. In some cases, strong convective cells lift large particles like hail above the freezing level, which can be detected by radar. However, 80% of the engine power loss cases studied, no returns were observed when the pilot was scanning the cell at 0 degrees tilt. Only when the pilot tilted the weather radar down to scan below the aircraft were returns visible. These ice crystals bounce off cold airframe surfaces. This is why no airframe icing is reported during flight in convective weather. When they hit a warm surface, like the windshield for example, ice crystals melt. Pilots have reported the appearance of rain on the windscreen, even at temperatures too cold for rain to exist. Pilots interviewed have reported that ice crystals sound different from rain when hitting the airframe. How do we recognize clouds with high concentrations of ice crystals? They occur in all types of convective weather, which lifts moisture to high altitude. Sometimes they can be recognized by their anvil shape. Sometimes we can recognize these clouds due to the turbulence or strong wind shear. They may produce lightning. However, these easy-to-recognize features are not present in most of the cases studied. The best way to identify these clouds is to understand that they often have heavy rain falling below the freezing level and producing radar returns, while at the aircraft altitude, no returns are visible. Concentrations of ice crystals can be found in all types of convection, from typhoons, hurricanes or tropical storms, to squall lines or even in an isolated CB. They all contain large quantities of moisture lifted to high altitude. Often, when engine power losses occur, the airplane was traversing a region where the cloud tops have reached well above cruise altitude, penetrating the tropopause. All these convective phenomena generate ice crystals. The density of the ice crystals is a direct function of the moisture in the low-level air, the altitude of the convection, and the proximity to the main updraft area, which may not be easily detectable on the pilot's radar. Some of these ice crystals spread out from the main updraft area in an anvil. These can form a hazard due to the high concentration, even at significant distances from a reflective core. Avoiding the convective cores is not sufficient to avoid ice crystals. In IMC, avoidance is difficult, and the radar will give little guidance. High reflectivity returns well below the aircraft may be the only indication of ice crystals aloft. This is an enhanced infrared satellite image of a convective cloud which caused an engine event. Cloud temperature is shown by blue, orange and white representing the coldest and highest altitude clouds. The aircraft track is indicated by green dots entering the cloud from the northeast. Pilots reported radar returns 20 nautical miles to the right of track. There was no turbulence and no radar returns ahead. After the engine event, the pilots diverted to the nearest airport. Below the satellite image is a representation of what this would look like in a radar cross-section. The highest cloud tops are associated with strong updrafts. In the vicinity of these updrafts, in areas which don't produce radar returns, we find high concentrations of ice crystals. This is a NASA satellite radar image showing a vertical cross-section of a convective storm. The reflective particles, such as hail, snow, and rain, appear colored. Only in the center of the storm, where a strong core exists, do these particles get lifted above the freezing level. The ice crystals, with an average diameter of 100 microns, are shown in white. This image illustrates that weather radar is insensitive to large regions of the cloud, where high concentrations of ice crystals can be expected. Let's discuss various effects of these ice crystals on the airplane. Let's start with the effects on the engines. The mechanism for ice formation inside the engine is thought to be the following. The crystals enter through the engine inlet, and bounce off the fan and nearby surfaces because they are colder than freezing. When the ice crystals encounter warm surfaces in the engine, they melt and wet the surface. Further impingement of frozen particles on these wetted surfaces results in a drop in surface temperature to the freezing point. At this point, ice can build up deep inside the engine core. Ice which sheds can affect the normal operation of the engine. This map shows the location of the engine power loss events investigated by Boeing. More than 60% of these occurred in the Asia-Pacific region. The explanation for this concentration of events may be that the sea surface temperature is highest in this region. The types of abnormal engine behavior which have been experienced includes surge, stall, flame-out, rollback, high vibrations, and compressor blade damage. The majority of engine events occurred between 22,000 feet and 39,000 feet, typically at tropical-like temperatures warmer than standard day, somewhere between ISA plus 10 and ISA plus 20 degrees Celsius. The flight crews reported visible moisture, light to moderate turbulence, and precipitation on the windshield, many times described as similar to rain but producing a different sound. They also noticed no airframe icing, little or no radar returns at the altitude where the engine power loss occurred, and on many occasions, incorrect temperature indication by the TAT probe. In some events, St. Elmo's fire was also reported. Now about the TAT probe. As discussed earlier, TAT anomalies have been reported on numerous occasions at the same time as the engine power loss events. It is now known that TAT anomalies occur in high concentrations of ice crystals. A TAT indication near 0 degrees Celsius during cruise is a warning that ice crystals may be present in high concentrations. The ice formation mechanism which causes TAT anomaly is similar to that which causes engine power loss. The ice crystals melt in contact with the heated TAT probe, producing liquid water and ice in contact with the sense element, resulting in a reading near 0 Celsius. Let's finish this module with a description of the effects of ice crystals on pitot probes. The icing mechanism which affects pitot is likely to be the same as previously described. The ice crystals melt in contact with the heated pitot and either block the drains or overcome the heater and block the inlet. Certain models of pitot tubes have experienced events. So far, pitot installed on airplanes manufactured by Boeing have had good capability in ice crystals. The best means to protect oneself against this phenomena is to know and avoid the conditions where high concentrations of ice crystals are likely to exist. Let's summarize what we have learned so far. Ice crystals have no effect on cold surfaces of the airplane. They melt on warm surfaces such as the windshield, engine components behind the fan, the TAT probe, and the pitot probes. In the majority of cases where these events have occurred, pilots reported the following conditions: flight at high altitude and visible moisture associated with convective clouds, ambient temperatures between ISA plus 10 and ISA plus 20 degrees Celsius, light to moderate turbulence, little or no radar returns, and no airframe icing. If flying in these conditions, the flight crew must pay attention to the airplane's position relative to the convective cloud. Note the wind direction and the likelihood that ice crystals formed by the convective updrafts may be dispersed downwind of the updraft. Avoid flying directly over the convective cloud. Use the radar tilt function to scan the cloud below the airplane. Where possible, avoid flying directly over amber and red weather radar returns below the aircraft, even when there are no returns at your flight level. In summary, if the crew encounters apparent rain on the windscreen at high altitude and/or a TAT indicating near 0 degrees Celsius at cruise, ice crystals should be suspected. The flight path should be changed to quickly exit these conditions. The crew should be aware that engine power loss and damage is possible, along with a possible thrust asymmetry. TAT or pitot anomaly may produce cockpit indications. A mental rehearsal of the procedures associated with these problems can help the crew be prepared in case the need arises. Thank you for your attention, and have a good flight.